Hi, everybody. Waiting a few moments for the attendees to slow down in the numbers rising. Great. Okay, thank you all for joining our last session of the week in the Chandra Frontiers in Time Domain Science. This is the second of our 2 Synergies sessions. If you had a chance to see yesterday's session, we did have a panel discussion. Next week's sessions includes a bunch of the topics that you see here. But I'd like to now actually ask the first speaker to share their slides, and I will introduce them. Our first speaker of this session is Darryl Haggard, and they are coming to us from McGill University and McGill Space Institute, and will talk to us about capturing the galactic center through Chandra's unique lens.
Thank you, Rudy, and good morning, everybody. It's a pleasure to be here with everyone today. Thank you very much for the invitation. I'm going to dive right in and just say how incredibly thrilled I am to be speaking this week on the very week that these fantastic scientists have won the Nobel Prize for their research on black holes. So George mentioned this at the end of his talk, and let me just say again that Roger Penrose, Reinhard Genzel, and Andrea Ghez were the recipients of the Nobel Prize, as you all know, and in particular for Reinhard Genzel and Andrea Getz's work on the Galactic Center. So here you see the UCLA group's incredible monitoring of the orbits of stars around Sagittarius A Star, and Andrea Getz's really inspirational quote about motivating other junior scientists to join us in this really beautiful field of study that we get to all be a part of. And so this is a perfect segue into my main topic today, which is really focusing on the galactic center and the supermassive black hole that resides there. So Sag A Star is sort of, we're going to put it in context here today since we're talking about variability and transient science accomplished with Chandra and other observatories in the Synergies section. Here's a plot from Jeff Bauer showing you the time scale for variability roughly in days versus the black hole mass for some of the supermassive black holes where we have monitoring. And you can see Sagittarius A Star down toward the bottom. It's around 4 times 10 to the 6 solar masses, and it has variability timescales that are sort of days-ish. So hours, 30 minutes to a few hours are the flares we see in the X-ray, and the timescales are of roughly that sort of size in other wavelengths as well. And also you can see M87, which is at much higher mass and varies over much longer timescales. So this is relevant for the studies that we do at X-ray wavelengths, and also very important when you want to try to understand what kind of cadences you need to look at for monitoring the black holes. So Sag A Star is convenient, not only because it's here in our galactic center, our local supermassive black hole, but also because those variability timescales are tractable for us to pursue on a sort of an observer's nightly or a Chandra observer's, day-ish or few day timescale. So I'm going to start off really highlighting the influence that the Chandra X-ray Observatory has had in this field. So Sagittarius A Star, as already mentioned, is a highly variable source. Here you're seeing its SED across a very wide range of frequencies, all the way from the radio out to the X-ray. And you'll notice, of course, that 2 places where we see quite a substantial amount of variability from Sagittarius A Star is at infrared wavelengths, and then here in the X-ray. And so you can see Sagittarius A Star's quiescent flux is down, and down here toward the bottom of this scale, and you can see that it varies by an order of magnitude or sometimes several orders of magnitude when it goes into a very bright X-ray flaring event. So what we'd like to do is to understand how to take the sort of largest scale view we have. So you're looking at a beautiful image here from the Chandra X-ray Visionary program. You're seeing a very scaled out view of Sagittarius A Star. This is roughly the Bondi capture radius. This is a Chandra image. And then the green contours over the image are the flaring emission subtracted out so that you can see the sort of underlying quiescent flow has a slightly elongated structure. And if we put that in the context of sort of a larger multi-wavelength view, this is a very zoomed out view of the galactic center. And you can see here sort of roughly a 20 parsec scale box. If you zoom in there, you start to see that S-star cluster that was on my shout out to the Nobel laureates area. So you can see here, these are the S-stars in orbit around Sagittarius A Star. And this haze here, the artist that was working with Jeff Bauer and I on this article, is intended to represent this very hot flow, this hot X-ray emitting flow around Sag A Star. And you can see these S-stars are punching through that flow as they orbit the supermassive black hole. And then down at the smallest scale, so we'd love to be able to observe this black hole all the way from the Bondi radius, these very large scales, out into these extremely small scales down at, a few AU, down at a few gravitational radii, to take a look at what's happening to the accretion down very, very close to the supermassive black hole, and whether some of this variability is driven near the ISCO, near the event horizon, and indeed whether or not we can identify a jet in this black hole, which is still a kind of an outstanding question about Sagittarius A Star. So this is that sort of aspirational goal in plot form here. So here you're seeing short shield radii going all the way in from the event horizon, very close to the supermassive black hole, out to the larger scales out near the Bondi capture radius. And you can see these numbers are showing you what kinds of constraints we have at these various different gravitational radii. In toward the inner regions, we actually use the size of the emission region and the SED to try to understand what's going on. A variety of different submillimeter and other polarization type measures. We can look at objects in orbit around the black hole and look for drag forces. Around the larger radii, sort of something like thousands of gravitational radii, that Chandra X-ray emission that I pointed out starts to be an important constraint on what's happening in the accretion flow, Chandra's luminosity, and then really understanding the stellar winds out here near the Bondi capture radius. So we'd like to resolve this entire range of gravitational radii or short tail radii, the entire range of densities, which can be also equivalent to a mass accretion rate, in order to understand this black hole in kind of all of its glory across all wavelengths. So this is our, as Andrea Gatz and others like to say, this is one of our very best probes of strong gravity in the vicinity of a supermassive black hole. And the fact that we can actually devise observations to span all the way from the Bondi radius to the event horizon is really quite phenomenal. And we're working hard to get you more information at each one of those kind of points along that plot. So just to go out to those large radii for a second, this is a beautiful visualization done by Christopher Russell in collaboration with Jose Quadra, who I heard earlier on the call, and Diego Calderon and Daniel Wang and others. And this is really using all of the beautiful multi-wavelength data that has been collected in the Galactic Center to try to understand the dynamics of the gas that's available to start the accretion process out near the Bondi radius. So the thinking is that those S stars that are in orbit around Sagittarius A Star are driving very strong winds. Those are feeding the gaseous environment around Sagittarius A Star, and coming in then at the Bondi radius is the sort of stellar wind component, which makes up the accretion flow, flowing on to this very, very low accretion rate system, Sagittarius A Star. So this is a beautiful simulation. You can find it on the Chandra press office, and you can zoom around. It's a 360 simulation. You can see bright outbursts from Sag A Star. It's really quite fun to play with. So then kind of taking the slightly less exotic Chandra press image. So here's another view of that multi-wavelength image of the Galactic Center. And here we're really highlighting in the little subpanel a very, very bright flare, one of those extreme variability events from Sagittarius A Star. You'll notice here that there's both a persistent source and a flaring source. So in yellow here, so these are a few time lapse. This bright flare occurred in 2013. This is the position of a persistent source that became very, very visible in 2013. It's a Galactic Center, the Galactic Center Magnetar. And this white circle here is showing you the position of Sagittarius A Star. So here in September 2013 and then later in October 2014 are two of the brightest flares we've ever seen from Sagittarius A Star. And they had to be bright for us to be able to pick up that flare sitting so close to the Galactic Center Magnetar. So this is really demonstrating not only how high contrast these flares can be, but also how important the very, very high spatial resolution of an instrument like Chandra's ACES instruments is to being able to resolve these two sources. They're only a few arc seconds apart. So being able to find their flux and really distinguish Sagittarius A Star's flaring flux during this Magnetar outburst was really very challenging. And it's extremely useful to have an instrument like Chandra to help us be able to do that work. So this is just a very quick slide highlighting the persistent source. This is the Magnetar. This is a beautiful piece of work just recently published by Chandra Rhea, showing you all of this amazing, Nanda Rhea, excuse me. I was thinking Chandra and Nanda at the same time. So this is a long-term light curve. This is the observed flux from the Magnetar over time. And this is sort of monitoring some of these neutron star. This is the luminosity of the Magnetar. This is the Galactic Center Magnetar in red. And you can see it's being contrasted with a few other very interesting magnetars, X-ray emitting magnetars that have been monitored over these multiple year-long timescales as well. And so you can see this Galactic Center Magnetar is really a beautiful example of a source that Chandra can pursue all the way down toward its very faintest fluxes and help us understand what's happening to this neutron star as it cools off from that flaring event. So then the other source that you could see in that little movie is that very, very bright flare. So this is a light curve of that extremely bright flare, which we called F1 in this work that we published just last year. And you can see this flare is interesting. It's double peaked. The black is showing you the whole flare envelope, and then the blue and green are showing you the hard and soft emission during the flaring event. These are just simple light curves. And this is the second brightest flare, F2. We plotted them on the same scale here. This doesn't look as impressive perhaps, but it's actually the second brightest flare we've ever seen from Sag A Star. And these two bright flares can be placed in the context of the work that Joey Nielsen and Mike Novak and others did, again from that Chandra X-ray visionary program, which really pointed out the sort of population of flares seem to have some sort of a correlation between the fluence, the total counts under the flare, and their duration. And whether or not these two brightest flares fit in that picture and exactly how we can come to understand that picture requires that we start to really understand the microphysics, the underlying physics that's driving these flares, so that we can try to understand the flare population as a whole, what's driving Sag A Star flares, what are the mechanisms underneath and that are operating in the accretion flow that are giving rise to these really large scale variability events. All right, so one way of getting at that is to try to look and see whether or not we can understand these flares at other wavelengths too. So we were fortunate to have, coincident with some of those X-ray observations, monitoring from the Very Large Array. So this is that same double peaked bright flare that you saw. Here it is in the X-ray. And in the purple here, you're seeing the VLA observations that we obtained simultaneous with the Chandra observations through the very excellent work of the teams, both at VLA and at the Chandra scheduling, in the Chandra scheduling team. So we do see a rise in the radio flux that seems like it may be coincident with the X-ray flare, but you already can see some of the challenges. The gray parts of this light curve are showing you times when the radio observations are less reliable. They're down kind of closer to the horizon, and we don't really resolve the peak of the radio emission, so it's a little bit difficult to tell exactly whether there were correlated events in the radio and the X-ray or not. There are some predictions. If we take this sort of peak here in the radio and we assume that that was in fact the peak of the emission, we can do a cross correlation analysis. And when we cross correlate the radio and the X-ray and do that exercise, we see some sort of a lag of around 120 minutes. But we wanted to be sure that this was robust. And so we took the X-ray light curves and the radio light curves, and we just cross-correlated them all with each other. So the panels in yellow down the diagonal here are showing you cross-correlations of two actually simultaneous light curves. And all of the off panels are showing you the cross-correlations for two light curves that are not simultaneous. In fact, they shouldn't be physically correlated at all. And in many cases, for example, in the case of that very, very bright flare, any radio light curve that you cross-correlate the X-ray with is going to give you some sort of interesting signal, or virtually any one, some of them as strong as the real signal. This is really indicating that the fact that the radio is very highly variable at all times means that drawing very specific conclusions about whether or not a radio event and an X-ray event are in fact consistent or in fact connected to one another, are truly correlated, physically correlated, is extremely challenging when our light curves are not long enough to fully resolve the rise and fall of both wavelengths of light. So that was one of the things we concluded from this. The shorter wavelength might lead the longer wavelength in this case, and this would be consistent with some of the models people have evoked for Sagittarius A Star, but the statistical evidence is weak in part because our light curves are sort of snippets that don't fully overlap. I should say the X-ray light curves are quite long, but of course we're limited on the ground to these shorter light curves of only about sort of 4 to 7 hours, depending on the particular night. So with this in mind, we actually a team of us proposed for some really awesome observations using the Spitzer Space Telescope and Chandra together. So when you have two space-based telescopes, now you don't have to worry so much about the diurnal sort of motions, our day here on the Earth, and you can do these very, very long stares. There are a whole lot of other challenges. Again, a shout out to all of the teams that helped us do the work of getting these two observatories looking at the same place at the same time. But here are light curves of Chandra and Spitzer looking toward the galactic center. The first two have shorter Chandra observations, but the last four here are showing you full 24-hour, fully simultaneous X-ray and infrared light curves of Sagittarius A Star. And now we can actually start to do cross correlations that are a little bit more robust and start to understand at these two wavelengths where we actually expect near simultaneity, or where if we could piece out a little bit of difference between when the peak occurs in the X-ray and the peak in the IR for flaring events, we might be able to start to get at some of that microphysics, some of the underlying physics in the secretion flow. And so this is work that was done by my graduate student, Hope Boyce, really a beautiful effort to take a few of you can see a couple of flares that are marked out here in the infrared, 1, 2, and then 3 and 4 occur in a single light curve, and cross-correlating these with the X-ray to see whether or not we see interesting, meaningful variability. And so Hope did that work really excellently. The top here you're seeing is the Chandra X-ray data. The bottom is the Spitzer light curve. And down in the bottom 3 panels are the cross correlations for these events. And you can see that indeed it looks like, so no lag, no difference between the timing for the two would be this red line here. And in all of these cases, it looks like there's a slight difference between the time when the infrared and the time when the X-ray peak. So Hope took this result and she also pulled everything she could out of the literature. And these are those flares that we observed in these really spectacular long 24-hour overlapping light curves. On this part of the plot, this way from the dotted line, you see the X-ray leads the infrared. On this side, the infrared leads the X-ray. So it looks like these are sort of hinting at a lead, again, with the shorter wavelength coming before the slightly longer wavelength. But I should caution that these are 1 sigma error bars. And so still here, we just don't quite have the statistics. We didn't get bright enough flares with quite high enough signal to do a really conclusive analysis of which one of these 2 wavelengths or how these 2 wavelengths are correlated. So it looks pretty tantalizing that the X-ray flares might lead the infrared by something like 10 to 20 minutes. But within our 99.7% confidence intervals, if you want pretty high sigma, they're still consistent with simultaneity. So these may be consistent with synchrotron models, which are some of the most popular models for thinking about what might be happening in the galactic center, though they don't rule out synchrotron self-Compton or some of the other models that people have put out there. Okay, so as I sort of close out here, we are of course now trying to push, as if you might remember that plot going all the way from the Bondi radius in toward the center. Of course, we'd love to push all the way down to the event horizon and start to understand what are the mechanisms driving these flares, and can we see whether or not those flaring outbursts are actually coincident with some sort of interesting substructure or orbital structure as mapped out by one of our amazing sort of horizon scale experiments operating today. So the 2 real players in this game are the Event Horizon Telescope, which you've all seen the spectacular results for recently, and the VLTI Gravity Instrument, which has also been just putting out beautiful science recently. So the EHT, you saw they're amazing, the collaboration's amazing, images from M87 just last year. And of course, we have been observing Sagittarius A Star with the EHT as well. And so those results are exciting, but still to come. So I won't be giving away any secrets yet today, but I will do a little bit of highlighting some really beautiful work coming out of the VLTI Gravity Group. So here you're getting resolutions of something like 4 milliarc seconds versus the 20 microarc seconds that the EHT can do. But this is still getting you very close to the event horizon and really getting you down to being able to start to look at the orbital motions of material near the black hole and try to connect that up to flaring phenomena. So this is the little press release GIF that they put out, a simulation of what might be going on if in fact we see hotspots, if it is indeed hotspots orbiting near the event horizon that are giving rise to these flares that we see in the X-ray and in the infrared and potentially also at longer wavelengths. So they did some of their first season of monitoring very close to the periops of the SO2 star. So that's one of the S stars that's in orbit around Sagittarius A Star. Both the European group and the US-based group are very interested, and both actually see evidence now for some precession of the periops for SO2, which is a beautiful test of GR using those stars orbiting around Sagittarius A Star. In this case, the gravity collaboration detected 3 near-infrared flares, and they found that their energetics were consistent with magnetic reconnection or potentially magnetic shocks between electrons and hot gas near the innermost stable circular orbit. The flare durations are consistent with the things that we see in the X-ray and the infrared, something like 3 to 90 minutes. And these are sort of similar to the cooling times for electrons if they're experiencing some sort of differential rotation. So this is really exciting. And of course, the gravity collaboration has not stopped there. So this is the first sort of exciting evidence for orbiting hotspots around Sagittarius A Star. And they've been thinking a lot more. I'm going to highlight a few pieces of work coming out of Jason Dexter's group within the gravity collaboration. This is some nice theoretical work by Michi Beobach, who has really been looking at sort of a hotspot in orbit around Sagittarius A Star. So here you're seeing a few different times in that orbit. So you can see here, maybe this is on the rise of a flare, slightly on the decline, or sorry, at the peak and then the decline. And then if you superpose all of those together and look at how that causes the centroid of Sagittarius A Star's flux to move around in sort of projected space on the sky, this is what that might look like. And so the cool thing about gravity is now you're really able to trace out the orbits of hotspots orbiting around the supermassive black hole. These are moving at a substantial fraction of the speed of light. They're consistent with the models that evoke sort of a Kerr black hole with something like 10 to the 6 solar masses, consistent with some of our other measurements of the mass of Sagittarius A Star. There's a whole suite of beautiful new polarization studies coming out of Jason Dexter's group and other people's studies, really starting to understand some of the magnetic components to the models and see what kind of constraints we can get from this beautiful new gravity work. So Jason Dexter's recent work really seems to support a magnetically arrested disk model. There's a lot still to learn from the polarization results. These seem to be consistent with an orbital radius. This is found here in the work that I'm highlighting here, as well as this other beautiful work done by Alejandra Jimenez Rosales, who's also working in the gravity collaboration. So these seem to be moving at an orbital radius, something like 9-ish gravitational radii, and also consistent with an inclination to our line of sight between the black hole spin and our line of sight of something like 140 degrees, which might sound a little bit funny, but that just means it's a clockwise spin compared to the line of sight that we have from our position in the galaxy. So if you're excited about learning a little bit more about these gravity results, there's really, really beautiful stuff coming out. And I think many of these papers that I'm highlighting here on this slide are just out in the last month or two. So of course, we're looking at this, as I said at the beginning on the title slide, through the Chandra lens. So what are we doing with Chandra? Of course, the thing we want is to be able to get these different observatories looking toward the galactic center at the same time. I've mentioned scheduling several times already in the talk. This is really a huge challenge from the perspective of our observatory teams. And so an enormous amount of labor has gone into trying to synchronize our observatories to look toward the galactic center so we can try to compare at different wavelengths. So this is that first early gravity result and a beautiful recent model from the work of Jason Dexter's that I was highlighting. And you can see that we've actually been able to start to kind of look in the real data at what these light curves look like. This is the polarization angle once again, and the data from this July 28th, this is 2018, these data were collected in. And then also we're attempting now to also observe the galactic center with Chandra and with, we can no longer do it with Spitzer, excuse for the misspelling of Spitzer there, because Spitzer is not around anymore, but we do have a few epochs from the last few years where we had gravity and Spitzer looking toward the galactic center at the same time. And so we're working hard to figure out how to compare those data to each other and see whether or not we can build up a consistent picture across many different wavelengths and observatories for what is the mechanism driving? Is this hotspot model of a sort of electron heated hotspot orbiting at the very close to the ISCO really the correct model, and what can that tell us about that temperature density profile in very close to the event horizon of the supermassive black hole? And of course, as I mentioned already, the Event Horizon Telescope is doing this work as well. And so the EHT is operating over the last few years. So we have observations in 2017 and 2018. Unfortunately, there were cancellations in 2019 and 2020. And so we're all very, very much looking forward to being able to collect these data in 2021 if all of the observatories can get back online after closures connected with the pandemic. So
3 minutes.
fingers crossed. Thank you, Rudy. I'm just about done. So fingers crossed that these campaigns that all of us have been working so hard to get synchronized can happen. Of course, we would be absolutely ecstatic if we could get the EHT, Chandra, gravity, all of the different very high energy observatories, all of the different longer wavelength observatories to all be looking at the same time, and then have Sag A Star bless us with an amazing bright flare. So if any of you are feeling sort of altruistic and you'd like to send us some good thoughts in sort of March and April of the coming year, please do that. We're really excited about where the science is headed, and to start to really be able to understand what happens in these radiatively inefficient accretion flows all the way down extremely close to the event horizon. Oh, and this is just, I just sort of jumped ahead a little bit. These are just a suite of the observatories that have been looking. So this is our 2017 campaign in collaboration with the Event Horizon Telescope. And you can see how many different collaborations from around the world are a part of that effort and are really trying to bring these rich data to bear on the questions about supermassive black hole accretion. Okay, so I will put up my summary slide then. Sagittarius A Star has been the subject of extensive multi-wavelength campaigns. We've been lucky enough to do some detailed study on a few very bright X-ray flares. And in both the case of the X-ray flares and in these beautiful new gravity infrared flares, we seem to find time scales that look like they're consistent with the flaring events happening at something like 10 gravitational radii. We did search in that very bright flare for some quasi-periodic oscillations or short time scale variability. We didn't find any very convincing evidence of that, but we will look again if we see more bright flares. And as I mentioned, we have done multi-wavelength campaigns. We see some tentative evidence that X-ray flares at the shorter wavelengths are leading the infrared wavelengths, but we're hoping that we can do a little bit better with that, looking in a new kind of 4 or 5 light curves that we have just over the last year. And we're working very hard to connect these things up to the actual mechanisms for electron heating and magnetic interactions in the galactic center to try to understand what's happening with the microphysics in the vicinity of the black hole and how is strong gravity playing a role there. So this is just all of these amazing, once again, to highlight the number of people and observatories and collaborations that are in on this work, and to say that we're working hard to understand accretion flows and to put very, very detailed constraints on models to see whether or not we can't refine them yet further as we go forward. That's all. Thank you.
Thank you, Daryl. That was perfect timing. It was excellent talk. We have a couple of questions from attendees. I remind you attendees, if you have a question, to enter it into the Q&A box down at the bottom of your screen or top of your screen, depending on your Zoom setup. The first question, thanks you for your good talk. And is from an anonymous attendee, and it says, it seems that in the plot you showed comparing the X-rays and IR emission, the latter had some structure, sometimes double peaked. Is there any explanation for this?
Ooh, you have good eyesight. Yeah, so maybe, I think, is the answer. We have wanted to, so you can see that double peak structure here in the X-ray. And then if you look in the infrared, you can see this little double peak structure in a few of these as well. And then I'll also show you one of my backup slides. So I showed this very quickly, but the polarization plot for the gravity, here we go, for the gravity team. So here is that very bright X-ray flare, and you can see it has a double peak structure. And the total duration of this flare is around 97 minutes. The time between the two peaks is about 30 minutes. And then this is that first gravity detection from 2018. And you can see, so this is a light curve showing that infrared hotspot going around. And this does appear to have a double peak structure and something very similar. So a slightly longer duration and also a sort of similar timed duration between the two peaks. peaks. And so there's a lot of interest in understanding whether these double peaked flares are showing us something about perhaps gravitational lensing of the hotspots in the vicinity of the black hole. You can get a more mundane explanation. You could just have a superposition of two flares. But if we see this double peaked, this sort of horn structure again and again repeated in these flares, I think we'll start to think it's connected not just to an accidental superposition, but some interesting, maybe probably gravitational lensing seems like one of the most likely candidates, or something else about how maybe magnetic reconnection has intermittent injection of energy to heat the electron populations in the accretion flow. So good eyes, great question, very exciting. I think we're still looking at the data to see what it can teach us about the double peaked flares.
Great. And we have another question from Harvey Tannenbaum. One of your plots, you had data you had a data point for G2. What did we learn about Sag A Star or about G2 from those observations?
Yeah, great. Also a great question. So I didn't actually pull out, I should have, thanks Harvey for asking, I should have pulled out the most recent paper from the infrared teams. So here's where I think Harvey is pointing out to the G2 work. So this was actually Stefan Gillison's work from 2019. And one of the things that people tried to do with G2, so we never detected any increase in the accretion rate or any unusual behavior from Sagittarius A Star in the X-ray. There have been several studies really emphasizing the XMM Newton data that say maybe there was an increase in the X-ray flaring rate. We did a pretty detailed study. Another graduate student of mine, Elie Bouffard, and I thought very hard about whether or not we saw that in the Chandra data. And we've never actually seen that when we just take Chandra, right, which can really distinguish Sag A Star and the Magnetar very, very well. We never saw any increase in the flaring rate there, but there have been hints of that. So that's the one X-ray signature. But one thing that's interesting is that the infrared folks have actually tried to put constraints on what the drag force would be on G2 and how that would change the orbit of G2 as they watch it evolve, and what that can tell us about the environment. Again, the sort of temperature, pressure, density in the vicinity of Sag A Star. And so that was the point of this paper, is saying this is a constraint that they thought they could put on by looking at the drag force on the orbit of G2 in the infrared. The other thing that came out just in the last year or so was a paper by Tuan Do, I think might have been the lead, about that very spectacularly bright infrared flare, which maybe had to do with a little bit of material that was sheared off of G2 and fell toward the galactic center, toward the event horizon, and created a very bright infrared flare. It seems to have been way brighter than we would expect just from the distribution of infrared flares we've detected previously. So they did connect that up potentially to something about G2. So we learned a little bit, maybe not quite as much as we had hoped that we would get out of that G2 interaction.
Great. One more question from anonymous attendee. Have the recent multi-wavelength campaigns helped constrain the spin of Sag A Star?
Yes, and I hesitate to say anything. Let me just say that I haven't taken enough time with those very recent works from the Gravity collaboration. And maybe I can just follow up, Rudy, and share if I go and scan again. So the early works that I've seen indicate that Sag A Star is not spinning it doesn't have a very, very high spin. You might have seen some of my slides mentioned a Kerr black hole taking a zero spin. What would that tell you about the orbits? But I don't recall the conclusions from those very recent polarization studies. So let me not put my foot in my mouth and just say that there are beautiful studies from the Gravity collaboration, all published in the last several months. And we should both go and look and see what the spin constraints are from those. I think a relatively low spin is consistent with everything we've seen so far.
Great. And there may be time at the end, for recapping on that
Great.
question, if you want to come back to it.
Super. Thank you.
Okay. We do have time for another question, and I'm going to ask a question real quick. It's the limiting factor on determining the lag that you're seeing, or is it lagging? Yeah. The X-rays are leading or lagging.
The X-rays are leading. Short wavelength seems to come before long wavelength. Yeah.
So is it the sensitivity that's the limiting constraint, and so you can't get the timing precision? Have you done any subarray mode observations in the Galactic Center?
So yes, so all of the observations, I think all of them that I presented today, we are working in the subarray mode because of the magnetar.
Mm,
So that magnetar is so bright that if we didn't work it, so we're working in a 1/8 subarray on chip S3. That probably means something to you, Rudy. But so it's a small subarray. So our timing resolution is something like 0.4 seconds. And we're in that mode so that we don't have too much pileup and contamination from the magnetar. At least we started that way. And then we've stuck with that mode in order to have really nice, consistent data sets since then. So so we are in a very small subarray for Chandra. And that was very useful for doing our timing studies on that very bright X-ray flare. But the main limiting factor is that most of the simultaneous data that we have, at least for Spitzer and Chandra, we don't have any bright flares. Sag A Star didn't grace us with some big bright outburst. And so we have very few counts, and it's difficult to do detailed timing. The infrared is fairly rich, and the X-ray, we just don't have very many counts to work with.
okay, thank you. Will the next speaker please prepare their slides? Our next speaker is Wynn Jacobson-Galan, coming from Northwestern University, and will speak to us about luminous X-ray emission from a calcium-rich transient.
Awesome. All right. Cool. So my name is Wynn Jacobson-Galan. I'm a graduate student at Northwestern. And today I want to share with you kind of an X-ray centered focus on the first calcium-rich transient that we've ever detected in X-rays, and how adding X-rays to the panchromatic picture gave us like an unprecedented picture, essentially, of where this calcium-rich transient came from and what we can do with X-ray observations and multi-wavelength in the future for this rare, peculiar class of transients. So before I begin, calcium-rich transients are a strange name, so I want to kind of give an overview of that before I jump into this specific one, 2019 EHK. Okay. Okay, cool. Sorry, my slides weren't changing. Okay, so what makes something calcium-rich? There's too many transients out there to count. There's so many different classifications. What's a calcium-rich transient? So before the name calcium-rich even comes into play, a calcium-rich transient class is actually an observational class. So its peak absolute magnitude is in the lower regime of supernovae. It's kind of in between a novae and an actual supernovae. And on the right, you can see the overlaid light curves of a bunch of different calcium-rich transients. The sample is pretty small, as you can tell. But what you can really see is that they rise pretty quick and they decline also very rapidly. And their peak absolute magnitudes are pretty low, indicating that they synthesize a low amount of nickel to power their light curves. And they also have a pretty low amount of ejecta thrown out in the explosion. So that's why they rise pretty rapidly. Spectroscopically, they're hydrogen poor, so they're type 1 spectra, and they usually show some amount of helium-1, so we have to reconcile that with exposure models. Their velocities are on the order of normal thermonuclear transients, so 6,000 to 11,000 kilometers. They're not ultra relativistic or anything. They're just typical supernovae, kind of on the lower side in the velocity space. And what actually makes them calcium rich is actually a name, I guess, associated with nebular line transition. So shown on the right is the calcium-2 nebular line, forbidden line to the forbidden oxygen transition. And as you can see, there's a lot more calcium-2 forbidden emission than there is in oxygen-1, which just means that this supernova type has just that little less amount of oxygen-1, so that's predominantly cooling through calcium-2. And if you take the integrated line flux, you'll see that the calcium-2 emission is greater than 2 relative to O1. So there's not necessarily more calcium in these supernovae. It's just that their emission is that much more prominent. So thus the name is calcium-rich, but you could also call them calcium-strong. And their location in galaxies is usually on the outskirts of elliptical galaxies, but this was based on really a low sample size. So now that we're discovering more, and I'm going to show you one that was found in a really nice barred spiral galaxy or spiral galaxy. And so we're finding them all over the place. So we have to reconcile that with the progenitor channels that we're trying to uncover. So I'm going to start with a pretty picture. This is 2019 EHK, the calcium-rich transient that I want to talk to you guys about today. It's in this beautiful host galaxy M100 at only 16 megaparsecs. And because the transient was so nearby, it represents the closest calcium-rich transient to us to date, and it was discovered only 10 hours after explosion. So that's the earliest we've ever discovered calcium-rich transient. It's the closest we've ever discovered a calcium-rich transient, and because of that, we get to just throw all the multi-wavelength facets we have at it, and we were able to study this from X-ray all the way to radio. And I just want to start with the in the optical before I get into X-rays, and start with just the classification spectrum. How did we even know what 2019 EHK was? We took a spectrum of the supernova at only a day and a half after explosion. And it seems pretty blue, featureless, kind of like a strange, I wouldn't even know what to call it right away. But if we look at this in a little bit more detail, we start to see really, really interesting features. So predominantly these features are actually narrow emission features called flash ionized features, which happens when the supernova shock breaks out of the stellar surface, and it essentially collides very dramatically with a circumstellar material, so gas that's been ejected from the progenitor star in the last days of before explosion. That will ionize this material. The material will recombine, and it will produce these really narrow peaks, which essentially are direct tracers of the circumstellar environment and of the progenitor itself in this type of supernova. So for a calcium-rich transient, we'd never seen this before, but this is just kind of giving you an idea about what we've already learned in terms of just spectroscopic evolution. So this is the first evidence that calcium-rich transients can have a circumstellar environment near their progenitor star at the time of explosion. So that's super exciting. But there's also other ways that we can probe this if we start to look at other wavelengths. But before I get into that, because this is a multi-wavelength talk, I want to go through the optical sequence a little bit in better detail. And so this is a video that just kind of goes through the whole sequence. And I'll just kind of walk everyone through what's happening. So that was the first spectral sequence. It's evolving. And what you see, it's already risen and fallen into a peak. So this is a double peaked calcium-rich transient. This is only like one of 3 that we know that has a complete double peak. And that first light curve peak is additional flux on top of the radioactive powered decay that powers normal supernovae. So this is an additional explosion mechanism. So some sort of other physics that's occurring that makes the light curve peak like so prominent relative to the radioactive powered continuum. And this fits really nicely into what I just showed you with the flash ionized lines, because a way to get a double peak light curve is to inject some energy into a pre-existing shell of material around the progenitor star. That will cause some increase in flux, and that will able to produce essentially luminosity on top of what's already there, which is from radioactive power decay. So like I say at the bottom, this double peak light curve plus these flash ionized lines are direct tracers for the first time of a circumstellar material and in the environment right around a calcium-rich transient progenitor. So that's super cool. So this was the optical UV and IR, but moving on to the high energy, the interesting stuff. If we look at the phase space of calcium-rich transients prior to 19 EHK, we see in orange, this is kind of how we've observed calcium-rich transients in the past and some other hydrogen poor supernovae. But what you might notice is that this phase space is really unexplored. So this is less than 20 days after explosion. We've just never gotten on target. We've never thought that maybe studying a calcium-rich transient that early was worthy of Swift time or Chandra time. But what 19HK showed is that calcium-rich transients are really, really bright if you observe them before 10 days after explosion and or in this phase space that I just highlighted. So 19HK is the first calcium-rich transient with a luminous X-ray detection at 3 and 4 days after explosion. And this is just with Swift XRT. So these were triggered observations, and because of Swift sensitivity, we just only saw detections at those times, and the X-rays faded really rapidly. So not only is that an observational constraint, but that's also an indication that whatever is producing these X-rays is actually really dense, compact material. And that what I'm going to argue is that that is the same material that's producing those flash ionized lines and that double peak light curve. So really we have one source for 3 different multi-wavelength components, which is really powerful in terms of constraining where this calcium-rich transient came from and what its environment looked like right before explosion. So since this is a Chandra talk, what could we do with Chandra if we had Chandra at the time of 19HK? Well, if we look at Chandra's sensitivity out to even 40 megaparsecs, we could have mapped this SED in the X-ray all the way down to its furthest, I guess, phase in terms of understanding what this X-ray luminosity was doing out to phases like 10 days, 20 days after explosion, whereas Swift was only sensitive to 3 or 4 days after explosion. So Chandra is the tool in the future to try to understand calcium transient X-ray phase space really, really early on. So it's going to be powerful in the future. So what did the X-rays tell us? The X-rays and the flash spectroscopy are probes of its pre-explosion environment, of 2019 EHK's environment right before explosion. So what I'm plotting here is a density versus radius plot for the progenitor environment of 19HK right before explosion. And what had never really been done before this study was that you can combine the X-ray and radio observations with this flash spectroscopy to probe this environment at really low radii, so at radii less than 10 to the 15 centimeters. And you're probing what the star has done, what it has shedded and ejected at the last days, the last months before explosion. And for a Calciumrich transient, this was just like unheard of. We hadn't been able to do this in quite the same detail as this before. But what you can see is that by combining flash spectroscopy, you get abundances of the circumstellar environment and then abundances of the star that exploded. And then X-rays, you start to probe the density of the shell that it ejected. And at radio, you start to probe at higher radii and understand if that shell extends far enough that the mass loss occurred, years after explosion. So what we found from these X-rays and flash spectroscopy is that this star had a very confined, dense shell of hydrogen and helium-rich material right around in its circumstellar environment at the time of explosion. And compared to other hydrogen-poor supernovae, we can kind of start to place the calcium-rich transient class in this X-ray phase space, this density phase space. And if we start to build up the sample, as I show on the right, we'll understand mass loss history in hydrogen-poor supernovae as well as calcium-rich transients if we start to observe X-rays earlier on. And we start to understand what the environment is like in the last days or months before explosion. So this is a very difficult thing to do, but it requires early time observations, which are key to constraining this environment and also constraining progenitors, which we don't know what they are, essentially.
3 minutes.
Okay, perfect. So zooming in, I said that 19HK is the first calcium-rich transient with a luminous X-ray detection, flash ionized lines, and a double peak light curve. This is 19HK in its host galaxy at 16 megaparsecs. So that's the closest calcium-rich transient we've ever had. But it essentially unveiled to us that we can now study calcium-rich transients in the multi-wavelength regime. So in X-rays, in radio, in optical on all sides, and we can uncover this beautiful picture, which is this artist interpretation right here, that calcium-rich transients eject some sort of material. Typically, if 19HK represents the calcium-rich transient class, it's hydrogen and helium-rich, it's dense and it's confined, so that's this purple emitting region right here, and it's essentially a tense ball of calcium-rich material and other thermonuclear products that are exploding and expanding into this medium. And that's the picture that we have. And without X-rays, this would not be possible. So what have we learned about 19HK and the calcium-rich transient class in general? So like I said, X-rays plus flash spectroscopy, so narrow emission lines directly probing the CSM, and the X-rays probing the density of the CSM are tracers of mass loss. We're now understanding that calcium-rich transients can emit X-rays, but we have to observe them early enough in their life cycle. So less than 10 or 20 days after explosion. And we've now understood that calcium-rich transient progenitors shed mass through mass loss. And this type of mass loss can then be constrained, can be used to constrain the progenitors of these transients in general. So more X-ray observations earlier on will be just instrumental in changing our phase space understanding of what are the progenitors of calcium-rich transients, what do calcium-rich transients progenitors do in the final days before explosion, and what does that say about the transient class in general? So I will leave it here. Here's the archive link, and I'll take any questions.
Great. Thank you, Wynn. That was a great talk. We have a couple of questions from the attendees. First, an anonymous attendee says, the calcium-rich is one attribute. Host galaxy location is a critical attribute, as is the presence or absence of helium. The existing data shows that 2019 EHK is a type 2b supernova and not a thermonuclear event like the classical calcium-rich transients. And there's a reference here for a D et al. 2020 paper.
Sure. So there are multiple interpretations of 19HK. Based on our study, it evolves and becomes a calcium-rich transient like all the others. It displays prominent calcium-2 forbidden lines relative to weak oxygen lines, so that makes it calcium-rich. It does not exist in the typical place of elliptical galaxy offsets, but a lot are discovered in various places, so I don't know if that's the best tracer. The hydrogen content is, I think, up for debate. There's hydrogen in its first spectrum, but that's from the pre-explosion environment, so that's narrow lines of H alpha. I think that a better spectral modeling will need to be done to understand if there's actually photospheric hydrogen, so hydrogen on the surface of the star at the time of explosion. But either way, if there is hydrogen, that's great. I think that works pretty well with our preferred progenitor model, which is a low mass white dwarf that has some sort of binary companion that is tidally disrupted, would have a little bit of hydrogen, a little bit of helium. So the 2B classification to me has to be a 2B for all time. And I don't think the 19HK is a type 2B supernova for its entire evolution.
Great, thank you. There's one more question. I don't think we'll have time to field it, so I'll ask you, Wynn, to either hold it for the end or to type a response to the question asker. And I'll ask the next speaker to start their slides. Our next speaker, let me introduce you, Tong.
Okay,
our next speaker
sorry.
is, no worries, is Tombaugh, who's coming to us from Nanjing University and will speak about periodic X-ray sources in the Galactic Center/Bulge, an application of the Gregory-Loredo algorithm. Take it away.
Okay, thanks a lot for the organizers, and it's been a great honor to be here. I'm Tombaugh from Nanjing University. Today, I would like to introduce my recent project about the periodic X-ray sources in the Galactic Center and Bulge by using the base-based method called the Gregory-Loredo algorithm. So I'll start from the background, why periodic X-ray sources matters and what can we obtain from their light curves. And then I will introduce the period searching in the Galactic Bulge and Center, including the procedures and the simulation. And finally, I will present my results and further discussion. So first, let's see some very interesting cases of periodic X-ray sources. The famous quark pulsar showing a double peaked feature in their light curves. And different things happen in magnetic CVs, consist of a white dwarf and a companion star. You can see there's only one peak in their folded light curve, suggests that the emission coming only from single magnetic pole on the white dwarf. Well, let's take a look at the orbital period, like the eclipsing of luminous extra binaries. In this case, it's around the phase of 1. So you can derive the mass and the radius of neutron stars based on the duration of the eclipsing and the depths. And the most puzzling one is the superorbital period of X-ray binaries. And I think the origin is still an open question, but the most accepted model would be the precession of the unwept accretion disk. So to summarize, the periodic X-ray light curves can hint for many properties like a magnetic field, stellar mass and radius, or even the accretion profile. So now for our galaxy, in this environment like a galactic center and the galactic bulge, the X-ray observations traces for close binaries like CVs and neutron star binaries, black hole binaries. And the stellar populations in this environment could be very different thanks to the higher stellar density and the presence of the supermassive black hole. So most of these X-ray sources are classified as CVs due to the higher abundance of white dwarfs compared to neutron stars and black holes. So the large set of CVs serve as great props for the parent stellar population, like dynamics, metallicity, and building history, based on their luminosity range, orbital distributions, and the X-ray spectrum. While only several CVs were reported before in these two regions with confirmed period that motivate us to get an more completed sample of periodic CVs. So our period searching is based on the data accumulated in the last 2 decades for the limiting window, a low extinction region sampling the galactic bulge and the nuclear star cluster locating at the galactic center. And our method is, as we mentioned before, the GL method plus validation by simulated results. The biggest advantage of GL method is the ignorance of observation gaps, which is well suited to irregular sample observation, just like in our case. As shown in this figure, you can see most of our observations are not centered and with casual exposure time. Secondly, the photon binning process is not required for the phase folding method like GL method, which will be suitable for source with only moderate photons like low luminosity CVs. So for the GL method, thanks for Gregory and Loredo presented this base method in 1992. I would not go deep into details for the consideration of time, just to present the key concept of multiplicity derived from the phase folded light curve, and the relation between the probability of periodic signal and the multiplicity. So you can see if the multiplicity is a really small number, the odds ratio, which is the integration over parameter space, would be a really large number, and the probability would be close to 1, indicating the existence of periodicity. So let's move on to the application of GL method. The first consideration should be the aliasing of non-periodic variations, just like shown in this figure. So you can see these 2 observations are with higher flux over other compared to other observations. That will be really dangerous for period searching. And the second and third is satellite dithering and city from time, which could be easily solved by just excluding the period signals around these 3 suspicious periods. But for the first one, we have to derive the false detection rate, false detection rate based on a large set of simulated light curves following pure Poisson process, but with the same long-term flux variation as the period candidates. And then we exclude the signal whose false detection rate higher than the 10%. So we also want to give an estimation of the detection efficiency of GL method by applying the 2 models to mimic their spin and orbital period of CVs. So to the first, the sinusoidal model, which mimicking the spin period of white dwarfs, we plot the detection efficiency versus the amplitude of variations here, and the different colors denotes for the different number of counts. First, we can see we only get adequate detection efficiency for counts over 100. You can see from the orange line. And also, as we expected, the detection rate is higher for more counts and higher amplitude. And secondly, for the eclipsing model, which mimicking the orbital period, the detection rate is really low unless we have many counts like over 1,000. And also for both of these 2 models, the detection rate is higher for longer period under the same circumstances. You can see that from the deviation of this 3 color line in the down panel, or the same color line varies among these 3 panels in the first figure. So also, the 10 sources detected before by Lamb-Scargill method have also been found by GL method here. So we can do the direct comparison between these 2 methods. Based on the 1,000 simulated light curves for each, we can see a better performance of GL method compared to Lamb-Scargill method for many of these sources. And for the results, we detect 44 periodic signals in 43 sources in the nuclear star cluster. And I present the typical case with white dwarf's rotational modulation here. The left panel shows the folded light curve. And if you remember, this is really consistent with the one I presented first, right? And the flux variation among different observations are presented in the middle panel. And the combined spectral with significant firing line emission, which is obvious for which is a typical feature for CVs, are presented in the right panel. And for limiting window region, we detected 25 periodic signals, and only 3 of them have significant iron line emission, indicating a poor metallicity here. And I present the one with eclipsing behavior and dual period. And we believe the shorter period here is a spin of white dwarf, and the longer one must be the orbital period, since we already see the eclipsing behavior around the phase about 0.5. And their positions in this region are shown in this figure. Also, we are able to give an estimation on CV's population in this region based on the efficiency we got before. So if we assume that all the sign circular variation only coming from the magnetic CVs, we are able to predict the number of sources that should be detected by GL method here, providing the source counts and the fraction of magnetic CVs. So when the fraction of magnetic CVs reaches about 23%, we got the predicted number equals to the detected number. And in that case, the number of sources versus the counts are similar distribution between the prediction and the detection. And also the fraction estimated here is similar to that in the solar neighborhood, which is 20%.
3 minutes.
Okay, thank you. And since we believe all these sources are periodic CVs, we should take a look at the CVs in the solar neighborhood. So CVs can be divided into non-magnetic and magnetic CVs. The latter one could be further divided into polars and intermediate polars according to the synchronization between spin and orbital period. So the evolution of CVs are driven by angular momentum loss, and that leads to a gradually shrinking of their orbits. The long period CVs whose period over 3 hours were dominated by the magnetic braking mechanism, whereas the gravitational wave radiation is for the short period CVs. So there exists a well-known feature named the period gap between 2 to 3 hours, within which the mass transfer was highly suppressed and fewer systems have been found. And also you can see from the sample distribution. And there's another feature called the period minimum around 80 minutes as a result of the donor star becoming degenerate due to the cumulative mass loss. Well, for our sources, you can also see the cut around the period minimum, further confirm that they are most likely CVs. While for limiting window sources denoted by the brown solid line, there exists an apparent lack of long period systems longer than 3 hours, which could be understood as an edge effect, since most CVs in the Bulge are highly evolved system and already shrunk their orbits. While for nuclear star cluster region, well, a quarter of them are with period lower than 1 hour, that may indicating a higher fraction of IPs compared to the solar neighborhood, or some of them could be accreting pulsars. Well, the more puzzling one is this separated population in the long period range. It could be a younger stellar population of CVs formed recently, or they could just be the low mass extra binaries. This is still open to discussion, and we're happy to hear different opinions. And I'll leave here and give the summary. I'll give the summary and leave out here. And thanks a lot for your listening. And feel free to ask questions, please. Okay, that's all.
Great. Thank you, Tong. That was an excellent talk. We have a question from Rafael Martinez Galarza. The Chandra source catalog 2.0 has Gregory-Loredo variability probabilities for all sources for which a light curve can be computed. Have you done a search of the catalog to either confirm your results or to find new candidates?
Well, really, we didn't have done that yet, but I think the variability done for this catalog is not concentrated into period searching, just for the variability check. I think it's not for period searching. The topic should be different, if I'm right.
So it might not give you the phase folded light curves that you're producing with your study.
Yes, I think I remember there is the variability check based on the GL method in Chow, but it's not for period searching, just to check for the variability. So it's just check for the very stars or the constant stars.
Great. I have a question for you. I noticed that you had an upper limit in some of your light curves you showed us. Can you use the upper limit in the Gary-Loredo method, or is it not
You mean here?
incorporated? A little
You mean
bit
here?
further down.
You
Further.
mean the yellow line?
No, keep going back.
Back.
Right. One more, I think a little bit more, a little bit more. Sorry, right here. Yeah, yeah, right.
Here.
I'm sorry.
Oh,
Forward one.
you
Forward
mean
one.
the
No,
forward
forward
one
one.
here?
Forward one slide.
Okay, sorry.
Or you passed it, but keep going.
If I
Here.
no, I don't think
There.
here.
Oh, sorry. Yes. So here you have two upper limits in that light curve. Are you
Oh,
using?
that because it's the counts are not enough for this observation, so I can only present the upper limits, but not the lower limit.
Okay, but
So I can
they're not incorporated into the Gary-Loredo algorithm.
yes, I mean this is just only for showing the long-term variation among observations. You can see this is different points for the flux in observations, not for our period searching.
Great. Thank you so much. I ask
Okay,
the
thank
next
you.
speaker to prepare their slides and share them. Our last speaker of this session is Jonathan Quirola-Vásquez, coming from Pontificia Universidad Católica de Chile, and is going to talk to us about extragalactic fast X-ray transient candidates hidden in the Chandra source catalog.
Okay, perfect. Can you hear me? Yeah.
Yes.
Okay, perfect. Thank you to the organizers for this opportunity to talk about my recent research. Yes, I am PhD student from Pontificia Universidad Católica de Chile, and my advisor is Professor Franz Bauer. So the X-ray transients play a crucial role to understand the physics and the mechanism behind a huge range of astronomical objects from stars to AGNs, and also covered a large time range from seconds to years. And in the next years and decades, several new facilities will be help us to understand better what is happening with this object. And the motivation of my work is related with these new X-ray transients, XT1 and XT2. These objects were discovered in the Chandra deep field south. In the case of the XT1 that you can see in the left hand of your screens, the host galaxy of this object was poorly constrained its redshift, how you can see in here, and also this transient show a fast rise in the light curve and also start to decrease with time to the minus 1.5. And the scenario that could be explained XT1, it's not completely clear. Probably the most reasonable scenario for this object is that could be related with the off-axis short gamma reverse. However, other possibilities, for instance, a tidal diffusion event between intermassive black hole and a white dwarf, are not discarded. And on the other hand, in the case of XT2, this object, here you can see the light curve, show a plateau during 1 or 2,000 seconds, and after that start to decrease with time to the minus 2. And also the spectra shows very interesting properties when it's softening with time, and you can see in here. And combining these timing and spectral properties and the properties of the host galaxy, that in this case is with a redshift of 0.7, the best scenario to explain XT2 is related with the Magnetar Wynn formed by the merger of two neutron stars. So this transient could be related with short gamma reverse. These two transients are very interesting, and the main goal of our research is try to find XT1 and XT2-like objects hidden in the X-ray archive, in this case, particularly in the Chandra source catalog, and also try to characterize them in different energy bands if it's possible, and also study their host galaxy properties and try to constrain parameters of them to try to find the origin of these XT1 and XT2 like objects. So in here you can see the light curve of ST1 and XT2 in unit of counts, and it is clear that these transients show a pull shape with a duration of 5 or 11 kiloseconds, more or less. And the idea of our method is try to find objects that have this pull shape light curve in the Chandra source catalog. Essentially, we adopt this Fred equation that you can see in here. This model is fast right exponential decay, very used in the case of the pulses of gamma ray burst, and consider this model and fit all the sources in the light curve of the sources of the Chandra source catalog, and consider different criteria related with the duration of the pulse, number of total counts, the background counts, and the counts before and after the pulse, try to find XT1 and XT2 objects. And additionally, we use another method, a Young method, which is more flexible to try to find objects that not necessarily have this pull shape. Yeah? However, we have a problem with this because these both methods not necessarily recover transient events. Another kind of objects like star flares, stellar flares, AGNs can mimic this pull shape light group. So in that way, we try to use additional X-ray catalogs to try to rule out non-transient objects. And in the same way, we try to use optical or near-infrared catalogs to try to discard stars or objects that was classified previously as young stellar objects, high mass X-ray binaries, etc. And try to find photometric redshift. If it's possible, try to constrain the properties of the host galaxies. So in here you have our results. In here you have in galactic coordinates the position of the events or the candidate detected by Fred, by Young, and the position of Chandra of XT1 and XT2. And the red stars are our final sample of 8 candidates to XT1 and XT2 like events that we found. In here, you can see the light curve of ST1, XT2, and also these new 8 candidates to XT1 and XT2 lab objects. And additionally, we studied this other X-ray transient, XRT 7831, which was detected or identified by Line et al. That this object is not part of the Chandra source catalog. However, only 2 of these sources, the green ones that you can see here, have a clear optical and near-infrared counterpart. So yeah, in here you can see the different images of these 2 transients in optical and near-infrared, and consider the photometric data of them was possible to constrain the redshift, but it's poorly constrained. In here you can see the photometric redshift that we obtain. So we need additional telescope time. We have the time, however, we have a delay due to the COVID outbreak. So it's part of the future work. However, it is important to mention these 4 candidates that you can see in these blue triangles. These transients show features very similar to XT2 in the sense that they show a plateau during 1 or 2,000 seconds, and after that a decay very similar to the decay of XT2. And additionally, they show a evolution in the hardness radio. XT2, if you remember, the XT2 has a softening trend in the hardness radio that you can see in here, and also this trend is more or less obvious in these other 4 X-ray transients. So we can associate these 4 additional transients like XT2 events. And if you remember, XT2, the best scenario to explain this is related with the Wynn Magnetar after the merger of 2 neutron stars. Additionally, we compute the local event rate of, consider 2 different cases. Case 1, in this case, the red star, it's considered the new 8 objects plus XT1, and the blue star the case number 2, it's only considered these objects that show similarities with X2. And also in here, we compare with local event rate of other well-known X-ray transients. In here, the color regions are short and long gamma reversed, and in here also the shock breakout events and also tidal disruption events. And it is clear that in the case, in the particular case of these 4 objects, they show a region covered by gamma reverse, and it is clear also a discrepancy with SBOs and tidal disruption events. So probably they are the subsample of 4 objects could be more related with gamma reverse. From here, I will only focus in this case 2 events plus XT2 and this other transient detected by line de Dol. So if you remember, these objects have very similar features to XT2. So in that sense, the idea is to try to compare with a well sample of gamma reverse. However, we don't have a redshift well constrained. So we assume 2 different redshift values, a redshift of 0.5 and a redshift of 2. Typically the mean redshift value for short and long gamma reverse respectively. And in here you have the light curve in units of luminosity of XT2, XRT 7831, and also this another object that shows similarities with XT2. And it is clear, similar to XT2, that this object at early times shows a low luminous if you compare with gamma reverse in general. And at later times, they don't have the same trend of the X-ray afterglow of gamma reverse. Gamma reverse decay like time to the minus 1.2, and they more or less decay in the order of 1.8 or 2, something like that. So they also don't share the similarities of the afterglow of gamma reverse that suggests that the origin of these objects are not related with the afterglow emission, essentially.
3
And
minutes.
also, yeah, thank you. And also, we compare with the light curve of axis gamma reverse that you can see here, which are still it's higher, fainter. So, following these ideas, if this emission of these objects are related with Magnetar wind, we can consider a wind Magnetar model given by this equation to try to find the parameter that could be explained the X-ray emission. So basically using this model, we fit the light curve of our events, assuming these 2 values of redshifts, and obtain parameters like the magnetic field and also the period of this magnetar. And here we have our results which fall in the region covered by long and short gamma reverse. We suggest that are reinforce the idea that they could be related with this kind of events. However, gamma reverse are not the only scenario that could be explained these objects. For instance, in this paper by Peng et al., they try to understand XT1 and XT2, consider a system of attended disruption events of an intermassive black hole and a white dwarf. And they obtain parameters that could be explained in this different paradigm. So in that way, we try to explore the parameter space in this new scenario to try to look if our events could be related with or not with this particular kind of tidal disruption events. Like a conclusion, we found a new eight X-ray Galactic transient in the Chandra source catalog. Potentially, we have a different kind of population of scenarios related with this new population of transients. We have also a subpopulation for fast X-ray transient that could be related with XT2 and essentially with the Wynn magnetar of after the merger of two neutron stars. And the next natural step is try to find similar objects in the archive of XMA Newton and Swift. Thank you.
Thank you, Jonathan, for that talk. It was really good, and I learned quite a bit.
Thank you.
I was going to ask you the specific question that you alluded to at the end, which is that you mostly studied using the Chandra source catalog, which I think is only has observations up to 2014. So it's about 14, 15 years of observations. And you found 8 sources, but I realized that the Chandra field of view is not as large as say XMM and the covering on the sky. So what
Mhm.
are your plans to roll out in that direction?
Okay, in that direction, the idea is to, uh, we are working on that at this moment, but the idea is, according with the previous papers, if I don't remember, uh, young adult try to find this kind of transients, and they expect, in the case of the Chandra source catalog, to find 15 events. And in the case of XMM Newton, if my memory is okay, it's a factor of 2 larger, the number of events that we can expect. So uh, we hope to find, in the case of XMM Newton, when we have a higher field of view, to try to at least improve the number of events in a factor of 2 at least.
Mhm.
But we are still working now.
Yeah. We have a question from Winbin Lu. Is the event rate that you predicted, which I think is 1,000 per cubic gigaparsecond per year, is it computed from z equals 0 or higher redshifts?
It's equal 0.
Z equals
In
0.
here, yeah, it's in redshift equal 0.
Okay.
Yeah. Mhm.
The other question I was thinking about is these types of transients must be showing up in E Rosita,
Mhm.
but
Uh,
maybe
mhm.
that you need more time there to build up a sample of such of them.
I'm not. Yeah, of course, with Erosita we can detect similar events, and in the energy range that we can talk in here, and yeah, we will expect to also detect in Erosita, but yeah, this is something that now it's outside our hands.
Right,
But
right.
yeah, yeah.
Okay, we have two more questions. Do you find any transients on shorter time scales or anything else? Because it appears that your sample is very homogeneous. So do you discard any transients? And this is from Dennis Alp, who also notes that they are working on something similar for XMM, and perhaps you two can discuss that further.
Yeah. I remember. Yeah, the paper of Alf et al. Yes, they discovered a new sample of 20 new X-ray X-ray transient in XMM, and some of them related with shock breakouts. Yeah, essentially, or criteria that also consider events with with a shorter time scale, because the idea is, at the same time that we try to find XT1 events and XT2 events, the idea is also to try to find shorter events that will be related with shock breakouts, which has a time in the order of thousands, hundreds of seconds. And yeah, both methods, Young method and this Fred method, they don't have a bias in that sense that eventually rule out X-ray transients related with shock breakouts or events at this short time scale. So essentially, we do not discard shorter events.
So from the 8 that you've gotten, you didn't get there by getting rid of an additional number of transients
Mm,
that weren't in your that weren't of the type you were looking for.
yeah.
Okay.
Mhm.
Great. We have one more question for you, but I also want to open up the audience questions for any of our attendees. If you have a question for one of the talks you've heard, be sure to just address it to that person in the chat box, I'm sorry, Q&A box. So a follow-up question from Winbin Liu is, what do we know about the host properties of these events?
Okay. Unfortunately, for this only this subsample of this interesting object, we have observational time to try to catch information of the host galaxy. From the archive, we don't know basically about the host at this point. In the next months, we expect to take spectras and photometric information to try to say something.
So you have approved time you mentioned, but it's been delayed by the pandemic.
Yes. Sorry.
Okay, if we have no more questions for our excellent group of speakers, I will thank all of our speakers for an excellent session on synergies. Um, I think we covered quite a range of topics in that group of talks, but I hope you enjoyed that all. And I'd like to point out that next week our sessions are listed here on this slide. If you're registered for the meeting, you will be receiving the email at the early part of next week with all of the links for the different webinars in that session. We have exciting stuff about stars, disk, and planets, solar system objects, massive and evolved stars, and we are going to have a communications and coordination panel discussion. And as usual, you can find all that information on our website. I hope to see you next week. Bye.